Okay, so we're back and we're going to go ahead and set up the sample scene here. Let's get rid of this stuff and let's start fleshing out our particles system. What we're going to do is create a birth on surface, and we're going to create some particle groups. What we want to do is we want to turn these pieces of geometry here, we want to turn the sphere and the cylinder into particles themselves, and then on their surfaces we want to birth some particles. So we're going to have one particle group here called source geo, and another group called surface markers. And for now we'll start with that and see how many more we need. So surface geo will make kind of a dull red, and surface markers will make kind of a nice bright color. Let's use our particle group manager to tell them both to display as dots. And actually, surface geo will have be as mesh. Okay, so to do this, what we're going to do is we're going to create an object particle. Pick our two particles objects. Say change effect all, turn you into the source geo group. Then what we want to do immediately is go ahead and access the surface position operator using the particle shape of those born particles, or birthed particles if you will. And what we want to do is go ahead and create a bunch of surface locations. And actually we don't even have to create the surface locations, we just have to tell, we have to use another position born with this count, and that will determine how many positions are accessed from this. So we'll feed that out of here. We might as well feed their alignment out. And we want this this whole process to happen for each and every one of these source particles who are being created. So we're going to go ahead and take the born particle and feed it into this position born particle input. And this basically means, hey, each and every one of these particles is going to call this entire function itself. So then we're going to tell that to be the surface markers. And you know what, let's trim up our names a little bit. Let's just do, yeah, surface markers is fine. And kind of a good habit is to turn your generators into, and rename them basically to the groups that they represent. Kind of makes it easier to navigate sometimes. Okay, so pistol shot for now, let's just do 10. We don't want to get too crazy. Long lifespan, oops, no speed, and no direction variation. Okay, let's go ahead and set up a memory, because we want each one of these markers coming out here to know which surface it was created on. So what we're going to do is set up a particle memory slot here called my parent. Its depth of 0 is fine. We don't need to remember a whole bunch of them. It's just going to be one parent. So the particle who's going to do the remembering, connect that, and who gets stored here in the parent, my parent variable, this of course goes back to the source. That's something else we do quite a bit, is actually double click the operators to remove any open slots. Sometimes that's easier in production because you don't get any confusion as far as which connections are required for your setup. On big setups it gets pretty hairy. Okay, let's pull up our layer manager here. We've got TP sources, it's our source geometry. Let's go ahead and hide that, get that out of the way. Okay, so here we've got, you can see our source geo in this red, and then the markers in the kind of orange. Let's actually push that a little brighter. Okay. And unfortunately though, we lost our helper object. Let's go ahead and throw him on the TP helpers. And this guy here, this box, is animated to kind of swipe left to right. Basically what we're going to have happen here is the box is going to kind of envelop these particles. Particles are going to detect, hey, I'm inside this mesh. When I am inside this mesh, I want to look around for other marker particles but I want to check and see, hey, are you on a different parent? Are you on this parent over here? So these markers here, even though they'll find markers on the sphere, we don't want them. We want the guys on the other side. Not only do we want the guys on the other side, but we want only the nearest one. And there's some very special things that we have to do to set that up. So this is going to get a little complex, but I'm sure you'll be able to follow along. Okay, so let's set up the in mesh rule. That's nice and easy. So surface markers who are in a mesh, whose position is in a mesh, my particle position. Remember in TP4 too, anytime you feed out a particle data type, you can connect that directly to this position input. You do not have to expose the position and connect that. That's redundant at this point. You can just go ahead and use the particle, and it will derive that particle position. Okay, we need a node. And remember, one of the biggest problems we see a lot is you throw in a node out here and you know which one you want it to be, but half the time we don't end up picking it. So always make sure you pick your nodes. Okay, so we'll connect that, clean that up. And of course, what do we want to have happen once that particle is in that mesh? Well, we could use the data channel. Basically, we want to set kind of a variable that says, hey, you know what, I'm in the mesh, I'm ready to be activated, some kind of switch or variable that tells this particle, hey, I'm about to do something, I'm ready to do something. So we're going to go ahead and this is another little production note here. We're going to create all of our memory variables on one memory operator. You can see we've got this memory operator here. Whenever you select memory, that memory is shown at the top of the list here. It shows you what variables it has. We're going to go ahead and rename this too so that we don't have any confusion about which memory operator holds the variables. We're just going to call it key. And we're going to set up a Boolean called activated. And we're going to use that here in the in-mesh test. So when I am in the mesh, I'm going to turn on this memory. And of course we need to feed in a Boolean that's going to set it to be true. Now of course you can wire this a little bit differently. You can expose the on for the Boolean and wire it like that. And thank goodness we have the debug capabilities here in TP. We can, actually we don't want to see that. What we want to see is whether or not the activated shows up. So bing bing, we start to see those get sent out here. And then of course if we want to try a different wiring method, we can use debug turned on and go ahead and just kind of scrub and see that it still fires out. So that's great. Kind of personal preference though, I like to turn on the memory operator itself. Okay. Got that set up. Let's go ahead and we'll go ahead and save this file. This is TP Advanced 4 PPassAB versus PSearch find nearest. These names might change a little bit, but they'll essentially be the same. Sometimes we like to add another index number in here to show where they are in a series. Okay, so birth on surface, you're in the mesh, and now what we want to do is we want the big kahuna. We want these particles to reach out and find some of these other particles. First method we'll try doing a PPassAB. And this is kind of an exploratory method. We already kind of know which one we want to use, but we just kind of want to show some of the issues that are going to show up with each one. So we'll use a PPassAB. Let's turn off our debug. And what we want to have happen is we want, of course, the source surface markers to look for surface markers. And well, we can actually make this work pretty well, but I can tell you already what's going to happen is we don't have a way to limit when these particles are going to be searching for each other. We can, and what I mean by that is we can't access this activated Boolean you can't use that activated boolean to control the on of the actual searching, because it's the actual searching between the two of them that takes up so much CPU. With just a few particles, it's not a big deal, but with thousands or hundreds of thousands, it's going to be a big deal. So we cannot limit ourselves, and we cannot enable ourselves to turn on this PPassAB at will. All we can do is we can check the outputs when these two find each other. So in this case, the PPassAB would say, hey, my first surface marker particle, if I am activated, and let's also get my parent, because we want to compare parents. We don't need the activated of the second one because it's not being activated. So if I'm activated and if my parents are not equal, so we're going to use a M3D condition here called is not equal. It's basically just a simple expression operator. It says if A equals B, then we're going to output false, 0. Otherwise output true, 1. So my parent, and then what we want to do is combine those two, because we need to test both of them. Are they true at the same time? Am I activated and these two are not equal? The parents are not equal. Then what we want to do is go ahead and, again, store with memory. We want to have this surface marker who's activated and found this other one who's not from the same parent. We want them to be, we want them to partner up. And in this case, what we can do here under memory key, we're going to create a new variable called my partner. I know that's a little close, a lot of the same letters as my parent, but I trust we can decipher that. So we're going to turn that memory on when those conditions are found. Okay, let's turn on debug, check our work. So what do we got? We got nothing happening. Actually, because we don't have debug turned on, or we don't have anything being exposed. Okay, so they start to find each other. Let's actually do this. Let's show both of them. And this is going to be part of the thing. We want to limit, so they only create one partner. We want that partner to be the closest other possible particle. But we do want this activated particle to search through each and every one of the other surface markers. We want him to search through each and every one and make sure that he finds the lowest possible distance. So right now, of course, that's not being done. We're going to get to that here in a second. But we also want to make note that once it finds that absolute closest other particle, we want that particle that it finds to kind of be taken out of the loop. We want it to be given a variable that says, hey, you're no longer available. Now, we could, kill it or switch it into a different group. I'm not really a big fan of switching groups a lot. It can be done, and a lot of times there's not a problem with it. But setting variables and tagging particles kind of allows you to not have to worry about any possible export issues or just kind of general tidiness, keeping your number of groups down. And that'll seem like a joke after you see some of the production scenes, which have huge numbers of groups. But and by huge I mean like 20. Okay, so let's actually carry this PPassAB a little bit further. Let's do a distance check between the two of them. So let's get their distance, and we're going to have to check and see if this distance is the lowest one found yet so far. And this is actually going to require that at birth that these surface markers are given a really large distance to remember. So let's see here. let's call it nearest distance. Fortunately, now we can also rename our variables here. So let's do that. Keep our consistent naming convention. So our nearest distance, we want to set kind of an initial variable value really, really high, so that whatever next one it finds, it's going to be less, and store that one instead. So what we want to have happen is we're going to compare the distance between these two particles and check it against my nearest distance. So let's expose that nearest distance. And then let's go ahead and say, let's get another condition here, is less than. Less than. So is my nearest distance, the last one that I've remembered, is it less than, or actually let's change that around, is this current distance less than my last stored value? Okay, and if it is, then we're going to go ahead and update that value. We're going to that partner there. Plus, what we're going to do is we're also going to update our nearest distance. Okay, so let's actually also show this nearest distance, and let's look at this distance. Let's actually also change our surface position so that we get a little, we kind of want to be able to easily see when this specific one particle is being activated. So we got here, okay, and bang, a whole bunch of stuff happens. So we go through all the distance checks. The distance that we found is 63.9. The particle, this guy here, is number 17. The partner it found, partner now is stored as number 1. Let's actually do this. Let's turn on our particle IDs. Okay, found number 1. And the next distance it found was 65, which is too high. It's not less than. Let's turn on our right to debug for that also. Okay, so 17 found number 1 with that distance. 17 found another one with 65, but it did not store my partner. That's why it doesn't show up in debug. Okay, but then it found a distance of 56, and so our out is true, and so particle 17 is the one who's activated. Now makes a partnering with number 3, which is the next one here. So let's see what else we get. We get 17 and 5, the distance 47, and then 47, we've got some numbers like 38, 15. So some of these should fire off. Let's take a look. Oh yeah, but you know what the problem is, that even though these distances are less, they are from the same parent. And so 17 is searching and finding like 15, 14, all these ones on the sphere, but that's not valid. We need that parent to be different. And so that's why this and out here is firing 0, or it was up there. Okay, so let's go ahead and clear our right to debug, turn debug off, and we're going to go ahead and we have to figure out if we can actually remove this other particle here from the pool of available particles. This is kind of tricky in this case, because while we could set up another memory variable here, and we'll call it a Boolean called available. Actually, we don't want to use it on this particular guy. We want to create a new one for our target particle. Okay, so let's think about this. If we've got our initial distance set up so high, the first particle that it finds with a distance less than the last stored nearest distance is going to end up storing that particle that it found, but also we want to take that particle, if it's the absolute closest one, we want to take that out of being available. So actually we don't want the available to be true, we want it to be false. So this brings up another good point. We have to set up this available here at birth. We'll tell all surface marker particles that they're available. Okay. And then not only that, but we have to actually check and see now, is it also available? So let's add this and make another condition required, and this available is also required. Starting to get a lot of wires crossing. That's going to be one of the things to get used to, is following the data. Hopefully, they'll add a feature where when you mouse over a wire it highlights or something. That would be sweet. Okay, but anyway, the problem is that whoever number 17 finds, it's going to be closer than the last distance, and so we cannot take that particle out of being available just yet, because we have to make sure that we compare it against each and every one of those other ones. And this is kind of one of the problems with PPassAB, that it may be possible to do, but it would require quite a bit of extra finagling and setting up a bunch of different extra conditions. And you might say, hey, just use the, let's actually measure our distance here. So spline tool is like the best way to measure. You just click the beginning point, click the end, and notice down here at the bottom of the status, it'll tell you your distance. Okay, so like 200 units is plenty to cover all of the particles who are there. So here's the problem. If we say find surface markers within this distance and only the nearest, what's going to happen? Well, 17 being so close to 16 here, 17 is going to look around and he might compare internally with all these other particles, but the only output that's going to come out is number 16. Let's go ahead and check that. Oops. Yeah. So here's part of the problem, is that PPassAB is constantly processing. So let's do this. Let's go back to the beginning. Okay, so particle 1 compares against particle 4. 1 gets listed again because it's got multiple connections. And then particle 2 compares against particle 4. So we can tell that this isn't going to work, just because the outputs here, it's only going to output the nearest pairing. It's not actually going to check each and every one of them. Let's turn that off. So that's going to be that's going to shut down our availability of using PPassAB at this point. So what we're going to have to do now is go ahead and change gears a little bit, and we're going to create a PSearch option, and we're going to see how we can get around that with PSearch. This is not to say that PPassAB is bad or anything, it's just that it doesn't work very well in a situation like this. So PSearch, what do we want to have happen? Well, we want the surface markers, when they're activated, remember, when they're inside that mesh. So when I'm activated, I want to call this PSearch function. And and it is the surface marker who's going to be doing the p-searching, so we connect that particle input. I want to search for other surface markers, and we could have just wired that into the group, but either way. And the distance, the radius again, has to be set for PSearch. So we're going to go ahead, and we know that 200 units is enough distance to cover all these. In fact, let's just do 300 to make it especially a good buffer. Just a little side note, if you're going to have a lot of particles and you're going to have them searching around for other particles, if the distance is really large, keep in mind that then you're going to have a lot of particle comparisons going on. It's nicer to keep it as low as humanly possible. That's not too important here, but again, in really big scenes, that can become a big issue. And I mean, as far as CPU computation. Okay, so there's the memory gets activated, calls the PSearch, and then what's going to happen is we're going to have to check and see. We're going to start doing a bunch of checks here. First, we need to see, we're going to need that distance and output. But not only that, but we're going to need to know if the surface marker that it found, if that surface marker is even available. That's kind of a big one. Okay, now this is something that we'll get into here in a second, is we're going to actually end up having to use the found PIDs to control this other memories on input, so that for each and every found particle that it finds, it's going to end up calling this memory function. If you don't do that, if you leave it disconnected like this, this memory is only going to fire once, and then all of the found PIDs are not going to be able to correctly compare their distance. We'll show that in debug here in a second. Go ahead and connect that. Okay, and of course we're also going to have to check the parents. My parent does not equal who I found's parent. So let's set up again. We could just go grab. So I should actually grab all three of these here. I think edit on the fly is turned off, so it's going to continuously update. We'll turn that on, so edit on the fly is on. That's going to require us to scrub, but it's going to stop TP from trying to process with every new operator we create. Okay, so my parent is not equal the parent who I found. This particle is available. And we want the found distance to be less than the last nearest distance that I've got. Okay, we'll get some creative wiring here. Okay, once we've got that set up, we can go ahead and store the values for the particle. We're going to set up my partner as an input and the nearest distance also as an input. So my partner is going to be connected to that found PID, and we'll describe all this whole flow here in a second. And that found distance is going to be, whatever's valid there. This memory only gets turned on when these conditions are true. Okay, let's see what we get. Okay, so what do we have? We have out first fired at 0, so something didn't meet the true condition. Out fired 1, okay, so these conditions are true. My partner was number 6, and then it found number 5, so it found these two here. Let's actually switch to a top view. So 6 and 5 are the closest So first it looked like it found number 6, who had this distance, and then it found number 5. But we don't see any other searches going on there. So that must mean that well, we do have a bunch of other zeros before that we step forward in time. But all these other zeros must have meant that the distance to everything else that it found was greater than what it had already found with number 5. Okay, so let's just run through the logic again real quick. Source markers, when they're in the mesh, they're activated as true. They call the PSearch function. They look for other surface markers within a radius of 300 units. And for each surface marker that it finds, this found PID is going to output that particle who it found. Okay. So each one of those particles who it found looks up and says, hey, am I available, and who's my parent? The parent's the easiest, so we'll check that. But remember, each one of these found PIDs actually has to call the memory and turn on the memory who's connected to that original guy who was activated. And that allows that memory to output its output multiple times. Let's go ahead and turn that off and just confirm and see what happens there. Well, maybe I was wrong. Although I'll tell you, I have actually seen that be required, so I'm going to stand by it. And we'll just go ahead and connect that. Maybe in this kind of wiring setup, this is actually a pretty simple little setup. Not to demean it, but some of the crazier ones with a lot of joint checking end up with a lot of operators, and in that particular case it had been required, so we'll just leave it like that. What do you say? Okay, so the next guy who gets activated here is number 16. 16, he found particle 6 and then particle 5. But now remember, we don't want that. We actually need to take number 5 out of the loop. And so this is where we're going to be able to do something that we can't do with PPassAB, and that is we're going to be able to check if the particle we found is the last particle out of all the ones that we found. The way we're going to do that is with the indexes and the count. And of course, because index is 0-based, we're going to need to, and count is not. So index, the last index is always going to be count minus 1. So what we're going to do is, and first in plain English, what we want to do is say, hey, if we've checked the last index out of all the possible found particles, the count that we found, if we've checked that last index, then what we want to do is go ahead and set the lowest possible partner that we found to be not available. Okay, we'll take a look at that. So what we want to do is we need to set up an integer with a +1 on it. So that index. And so if our index is equal, so we're going to use a condition is equal. Okay, if our index is equal to the count that we found, then I'm going to go ahead and I want to set the last good partner that this guy found to be not available. And the way we're going to access that is we can just pull it right out of this memory here, and where we can say my partner as an output. We're going to set this memory. I'm going to connect that to my partner, and that is going to have a available input, which is going to be false now. Get my mouse to work. Available, false, so we leave that blank, and that is going to fire and be true when the number of the particle that I've just compared against is the last one out of all the ones that I found. So because the index is 0-based, it's always going to be 1 less than the count, so we add 1 so that they're even and the same. And so when those two numbers are equal, then we're at the highest number in the count, the last index, and then we turn on this memory for our partner. We're actually storing these partners all the time. Anytime we find a new one with a lower distance, we go ahead and just store them. And then once we get to the last index, matching the total count, then we set that partner to be not available. Let's go ahead and see that in action. Let's do this. Let's say, we'll show that, turn that off, and also we'll turn on this, and let's found index and found count, sure. It's going to be a lot of numbers flying out, but okay. So what do we have? Found index is the found index. So remember, this is actually what it means is the found index number that I'm checking against, or the found indice. And my found count is 19. So the particle who's doing the checking here is number 17. You can tell that because the memory input, this is the input symbol here, these two less than signs, refers to it's an input being on the left side. So that particle there, getting that 17. My partner is an input, so the found PID that it must be checking is number 6. So I found this guy. That's his distance. So it gets stored here in nearest distance. And then next up we have the found index is number 1. So this the next particle that it found. Total count again is 19. Remember, it outputs this stuff for every iteration of every particle it finds, all in one time sample. And then what we've got is the particle 17. That's particle 5. That distance is 47. It's less than 56, of course, so we go ahead and store it. And then all these other numbers here, the index, the count, etc. This is showing us all of the indices coming out, but none of them match all these conditions that we need, where the distance is less than what we already found, and where our parents, there's the distance, and our parents are not equal, meaning you're a marker on a different parent. Okay, so available 0 finally gets fired. So we could also, put that out there so we can see who that was. Let's go ahead and just do that. Okay, so particle 5. Particle 5 is now at a 0. Let's make sure particle 6 did not get a 0. Yeah, definitely not. Okay, so next, what do we expect to have happen? We expect particle 16 to find particle 6. That's kind of hard to tell. Maybe it's 3, but I believe it's 6. So let's see what happens. Oh, and you know what? This is actually, you can tell by our debug output, what's continuing to happen is this comparison's going on again and again. The surface marker is actually still searching every time and doing all these updates. So this is going to eat into our CPU a little bit. What we're going to do then is go ahead and we'll just duplicate this. We'll set this particle who's doing searching to also not be available. So then we're going to need yet another check here. We're going to need to check and see, hey, is it available? And then we'll need one more AND input to make sure that, hey, the guy who's doing the searching, is he available? That's just another condition that we need to require. Okay, now we've got a real jumble of wires there. It's tough to tell what happened, but or tough to kind of decipher, especially since we tend to organize our space like this so that we can keep it all on one monitor. But we'll make do. Okay, so let's actually go back. Oh, we need the on input, of course. Let's reset that. Get our outputs here. Ba-boom. Okay, so what do we have? We've got particle 5 becomes available 0, and particle 17 also available 0. Now let's see what happens as we step forward in time. All we should see is the little green time indicator. But what we are seeing is, oh, you know what's happening? It is actually going through and still calling the PSearch function. What we have to do is actually set our available out here. Let's say I am activated and I'm available. Use that to turn on the PSearch. That also means we can take off that other output there, because of course it is going to be available coming out there. Oops. Yeah, reset that. Go ahead and step through. Okay, fires off, still finds number 5. That's a good sign. Okay, so now as we step forward, all we see are the green time steps, and that is because this surface marker 17, he is no longer available. So he might be activated, but he's not available. So this AND results in a false. It only results in true, of course, when it first gets activated the very first time. But then once he's gone through and checked through all the available indices, the other particles that he found, then he finally gets turned off available. Okay, so let's see what happens. So we know that 17 bound with 5. Let's see who 16 binds to. It looks like 16 is going to bind with number 3. So particle 3 becomes not available. Okay. Let's see if that makes sense. 16, yeah, closest distance probably would be number 3. Okay, another easy way that we're going to set this up so that we can kind of check and make sure, let's turn off our debug outputs, and clear the debug window, turn it off. What we're going to do is just use a simple bring to then at the end of this, where what we want to do is, of course, once the surface marker, and we can borrow a bunch of logic out of here. Let's just grab those 3. So if I'm activated, and actually we could set it up and say I'm not available, meaning I've already found somebody. That would really be kind of the best way. So let's go ahead and do that. I was going to try to cheat, but oh well. Then what do I want to have happen? If those 2 conditions are true, actually we don't even need this one. What we can do is we can just grab our my partner. I'll put that there. And say dynamics bring to who's going to be brought, and what position and alignment are we going to bring to. Okay. Let's go ahead and save while we're at it. Just always a good idea to save and keep our. So let's kind of watch and see who's flying to who here. So they should progressively go further and further. That all looks good. Now PIDs are actually a little bit slow to display, and we're going to increase the count of the particles so we can really see it in action. So we're going to turn all that off, and let's go ahead and say create 500. And what we'll see is that the particles on this side, as they get further and further over here, are going to have to go further and further into the cylinder. Pretty much what you would expect. Now we should display them actually as dots. Okay, we got no override. P group. Surface marker dots. There we go. Okay, now you notice that we are getting kind of a lot of stepping in the velocities, where they kind of form these line patterns like that. We're going to want to try to adjust our timing there. anywhere between, say 20 and 50 frames. And we don't want it to be per call, of course, because we don't want these surface particles who are flying over there to decide every time sample, every call / every time sample, what their evaluation time should be. We only want it once for their animation, so we set it that. So now we get a little bit better variation in there. We could change that up a little further, either with most obviously with changing the time sampling. Some other things we could do is put in some variable friction, but we can see how they fill up from left to right. Okay, so yeah, taking a look here, PPassAB, we got pretty close with it, but again, it broke down as we were trying to make sure that we checked every available pair, which is something that PSearch allows us to do with that index and count. PPassAB, of course, it does give us, we don't have any here, let's set one. PPassAB does allow us to access data channels directly, which is kind of nice. Something that PSearch natively does not do. But of course, a workaround for that, you remember, is just anytime you've got a particle who's got a data channel, just create a rule, take that data channel, and stick it in memory. So every frame, and actually you could do it before the PSearch. We'll call that store DC in memory, or mem as we like. And that'll just take whatever value is in there, and it's going to go ahead and pipe it into that memory. Unfortunately, it's going to do it every frame. You could probably set up a check to see if it is if that value has changed, but we'll skip that for now. Remember, of course, also that the advantage of data channels is that they are actually cached when you save a cache. Memory values are not cached. So if you end up having a memory value that you need to store in a data channel so that it gets cached, and remember those values are updated per time sample, so they can change over time. One of the easiest things available to do is just set up another rule similar to the store DC in memory, but here at the end we could say store mem in DC. Store mem in DC then is just going to be a turnaround of that, where we will take the memory value, that scalar. Let's actually rename that to something coherent. Let's call it scalar float. Let's call it float DC. Okay, so float DC, not as an input but as an output. Don't need the depth. And then just go ahead and store that in a data channel. Data channel 0, of course, since that's what we have set there. So in this way, every time sample, we're storing our memory value into our data channel, so that any change in that time sample, if that value changes, is actually going to be put into a data channel and stored with the cache, because only data channels get stored in cache, no memory. Okay, so that was kind of a little bit longer of an example, but we covered quite a few things, so let's go ahead and move on.